first of all, it's an honor to be here. And I was told that this is going to be recorded. And I just want this for the students, to be honest, because it's a little bit embarrassing that if I made a mistake, somebody goes in slow mode and try to check what I said, right? But anyway, I hope that the good messages still are passed around. So yeah, I'm going to talk about MeV neutrinos because as a nuclear astrophysicist, I'm interested in several questions, and all of them are kind of tied with neutrino physics. So one of them is that how the heavy elements in the universe are made. And another question is how the stellar explosions happen, how are neutrinos related to that. The other question that is very interesting as well is the structure of nuclear matter. So we know about the nucleus, but when we go to heavier and heavier nuclei, then the structure of the nucleus starts changing. It can take shapes, and like tiered shapes or football ball, the football shape. This is the one that you're gonna go slow down in YouTube and you say, oh, that she made that mistake when she was speaking. Okay, so how is this neutrino in these environments are related to the behavior of very dense matter? And it's, you know, as neutrinos propagate or decay or are a byproduct of nuclear decay, they are also emitted in very dense environments. And by that, the best experimental setup are neutron stars. So neutron stars are profoundly connected to neutrino physics. And well, if you don't know, I guess that I see very young faces here. So I'm going to go ahead and tell you a little bit about what a neutron star is. And a neutron star is, occurs when a very big massive star, like 8 times or more times heavier than sun explodes and collapses by gravitational collapse, and there is no any more nuclear fuel that keeps that collapse that halts it. So there is this balance and between the hydrostatic equilibrium, between the pressure, outgoing pressure, and the collapse is gone, and the only thing that is remaining then is this core that is very highly dense. So that's what is a neutron star, and in all that process, a lot of neutrinos are emitted. The vast majority of energy is emitted through neutrinos. So to give you a perspective of this, I did this little cartoon here that shows you that here's where we are right now, and I just went to that direction because I found that more people are living in that direction than in the other one. Point is that this is the greater Keystone area, right? So you can see that in a radius of 12 kilometers, this is kind of what it will look like a neutron star, and then you put the mass of the sun there, and that's how dense they are. They are extremely dense objects with densities that reach 15 grams per centimeter cube. And to give you an idea of how dense that is, I just put the density of a lead. So it's orders of magnitude, 16 orders of magnitude larger. So I was telling you the story about neutrinos because as neutrinos are released from the birth of a neutron star, then we can know, kind of understand how the supernova explosion happens. But that's not the only scenario where we can get to know about the behavior of stellar explosions. Gamma ray bursts, for example, are also connected to neutrinos. I already commented about the nucleosynthesis. So what else we can study? We can study diffuse neutrino background, and that's part of what I'm going to be focusing at the end of my talk today. So there are 3 different aspects that I want to discuss with you. So this is a cartoon of how I understand my own field. And I know there are several people here that are doing a lot of astronomy, astrophysics. There are also a lot of people that are doing neutrino physics. So I just wanted for the non-expert to give you an idea of how I see that I belong to, so you can understand where you may be in the world as well, or where, you know, if you after graduation or something like that, you decide to keep doing physics, then maybe you fit somewhere in one of these boxes. So this is my flow diagram of science, of nuclear astrophysics, let's put it that way. So I can start for observations. There are many observations that we don't understand. For example, the synthesis of elements, okay? We can try to understand that via nuclear physics, but we need really an astrosite. So let's try to have some connections with the people that do numerical relativity or hydro simulations, and out of that, there will be some data that is produced. From that, I can get some thermodynamical variables, temperature, density, etc. And with that, I can do a post-processing of these simulations. That's what I do, okay? I do a post-processing, and then I get to know how gravitational waves are generated or how neutrinos are generated. And for that, I get back to, do I agree with observations or no? So I'm going to touch into a little bit of these boxes here, but I'm going to, of course, focus a little bit on nuclear physics and neutrinos. So the observations nowadays is very, we are in a growth of information, so it's connected to multi-messenger, so I'm going to talk a little bit about that, but I want to tell you that one of the things that observable that has been there for a while is the abundances, the element abundances. Okay, so what you see there is a diagram that shows you the abundances related to silicon, and in the x-axis you have the proton number. Okay, I just highlight in red some elements that we are familiar, like with, like the common person in the whole can tell you about oxygen, awesome, or maybe gold over there, or uranium more for the nuclear physicists, and so on. So this is what we know, but what we don't understand as nuclear physicists is why the intricacies of this pattern. What we kind of understand the orders of magnitude here in this axis compared to uranium. Okay, we understand kind of that, but how much of each is produced in the universe, we don't know. We haven't been able to explain that. That's one observation that we haven't been able to understand as a community. But now that we have so incredible capabilities for observation, astronomical observations, we have many more. So I'm just highlighting here a few of things. So if you are working an experiment or some setup that is not mentioned here, I'm sorry, I just don't have enough space to put them there. It's incredible the amount of data that we can collect. So we have observatories in the visible light, we have X-ray, gamma rays, we have gravitational waves, and we also have neutrinos. And I know detecting neutrinos is very difficult, but it can just help to understand the whole a system as a whole. So it's part of the puzzle. Okay, and I think that you, I would dare to say that perhaps you've been familiar with this, the neutron star merger that happened in 2017, and this is one of the biggest papers that came out of that observation, and I'm not gonna go on the details of all the gravitational or gamma ray bursts of visible light or non-visible light, but infrared and so on. But I want you to take from this is that the light curves show us that at early times, there were elements produced with a number, mass number, meaning the number of protons and the number of neutrons are a little bit less than 140. That would be in, what is the silver? Silver, I couldn't find the word silver, okay. And the late time evolution, meaning after days or weeks, then gold was produced, or beyond that. So there is a change in the number of mass, and that could be correlated to neutrino physics. So there is some potential here for understanding why this happened. Now, there are tons of references to these papers. If you are interested, you could see. That's what observations told us. Let me go back a little bit so I bring you back to context. So I told you that we have tons of observations that need to be explained. I told you that I haven't told you anything else. I'm going to tell you about the simulations. What these simulations tell us? Well, simulations are, there are different groups around the world that are working with different tools. Some simulations are hydrodynamical, some others are steady state, one dimension, three dimension, relativistic, Newtonian, etc. But what is more amazing is that they were already telling us before the first neutron star merger was observed what happened. Two neutron stars get closer to each other, gets in a spiral moment where a lot of gravitational waves are emitted, and then the temperature increases. What you're seeing here is a scale of temperature, and in that moment, a lot of neutrinos are being produced. As matter is getting like detached from one star to the other, neutron matter is decompressed, interacts with the neutrinos, produces heavier elements, and then finally, this old star becomes one central object that is called a hypermassive neutron star with a disk accreting around it, and essentially the neutron star collapses at some point to a black hole. During all that time, matter is being ejected, and then more heavier elements are produced. Okay, so that's what we knew. So essentially, the 2017 event was like a victory for the modelers. We say, yes, that's what we kind of had predicted. It was really rewarding. Now, I have talked a little bit about this. I have talked to you a little bit about this. So what nuclear physics tell us? Well, nuclear physics can tell us many things, but I'm just going to talk about this neutron stars or dense matter business right now. So one thing that I will need to make a case is to talk about the R process, okay? So there are elements that are naturally radioactive, and when they decay, they can decay by beta decay, meaning either emitting an electron or a positron. But this kind of a similar event, which is neutron capture, is similar in nature, in the way that weak interactions happen inside a nucleus. So a neutron can be captured by a nucleus. That means the mass number here increases by amount of 1, and then that neutron, you can think about it, converts into a proton inside the nucleus. That's why the proton number here increase. And then we will have neutrinos, which I didn't put here a cartoon, and then gamma rays, and then an electron. Now, the cartoon is just very a rough idea. Point is to imagine, to understand this problem, we need to understand how the nucleus behaves itself to be able to capture a neutron, then how this compound nucleus behaves in terms of energetic states, so they can emit gamma rays and decay somehow. And then we need to understand how this reaction is happening, how likely it is to happen. And a very important point is that in stars, like neutron stars, merging, there are so many neutrons around that is very likely for neutrons to be captured before that compound nucleus decays by beta. That's why it's called the R process. Many neutrons are captured, and faster than beta decay is possible. So that's why we call it a R process. And yes, it produces neutron-rich nuclei, because then at some point all these neutrons are being captured in the nucleus, probably after some beta decay, become a nucleus that is stable. It doesn't decay anymore. Okay, so a rich mass number is done, is achieved. So why is this a challenge? Well, it is a challenge because, as I explained, I just told you that this compound nucleus is a complex system that we don't understand, and we don't understand it because the character of the nuclear force is unknown. Okay, so it's not like you know gravity, you know mass 1, mass 2, divided by the distance squared, etc. We cannot write that in nuclear physics, and the reason is because it's a residual force from the color force. So there is no one here in the community that can tell me, okay, use this potential and I know I'm right. Because maybe the person is okay for low mass nuclei, but not for large mass nuclei. So there is no consensus about the nuclear force. So it's what can we do? What we could do is experiments. Try to shoot things at each other and figure it out. There are capabilities around the world that allow you to do that. And develop theories. So we can develop theories and compare with experiments and see how we're doing, or we can do and take a look at the most gigantic nucleus we ever known. which is a neutron star. And why I'm saying this is because the density of a neutron star is, oh, it got cut. Oh, my punchline. Okay, here it says that the nucleus density was 10 to the 14 grams per centimeter cube. Okay, that's the typical density. I should have noticed that. Okay, so what we do when we study the largest nucleus out there, or the interactions of the largest neutron stars colliding with each other, we get to know, for example, we can develop models for reaction change, reading a lot of neutrons coming to different nuclei and see how they decay. They form a reaction of a chain reaction and see what happens. So look at this. This is what I'm talking about. If we are going to plot a figure to study that, this is like the modern periodic table, if you want, in nuclear physics. Here is that what we have in terms of neutrons and protons, and every single pixel here means a nucleus, okay, that either is measured or predicted by theory. Calcium 40, for example, I cannot be steady enough to show you there, but that's calcium 40, and it's a stable nucleus. Now, all these colors is just telling you how fast they decay, how fast this nucleus decay by beta or whatever, this is the half-life, okay? So meaning the darker the color here is more stable. This is very unstable nuclei. And what happens if we have an R process, then neutrons are captured, meaning that we will follow this kind of magenta line in terms of captures. Every time a neutron is captured, then we move to a higher mass number or higher neutron number. So we capture, and then new beta decay will happen, so we will move diagonally in this nuclear charge. These bars correspond to what we call in nuclear physics the magic numbers. So nuclei that are more difficult or last longer, okay? So if we find what will be the final abundances after the nuclei have decayed, then we have these magenta squares here that are now displayed here as mass number and the abundances. So this is the analogous of the figure that I showed you in blue and red at the very beginning of my talk. Essentially now it's a mass number. So we know that from doing simulations of our process abundances. Why neutrinos? Okay, because neutrinos interact with protons and neutrons, and they can change the ratio of neutrons to protons. So if we have less neutrons, the closer this magenta line will move towards stability, towards this stable nuclei. If we have many neutrons, then the closer we will go here, and the heavier elements are going to be formed. So neutrinos have the very important role to set the number of neutrons that are available for the R process. That's a very important punchline. And the last piece of nuclear physics that I'm going to talk about here before I move more into neutrino results is about the nuclear matter equation of a state, which is a big unknown, again for the same reasons, because the nuclear interaction is not clear for anybody. So the equation of a state is just a relation between thermodynamical variables. Like for a free gas, is PV equal NKT, okay? Here, N being the density of particles that you have, and you're assuming they are not interacting between themselves. Now, we can assume that neutrons in a container are a Fermi gas, and when we do that, then we can reach to what we call the polytropic equation of a state. This N is the polytropic index. I should have used a different character here. It's not the same as the density. So polytrope are very important and are very much used in the simulation community to get some results about how the merger will happen. So this, one of these, if you Google, for example, movies with simulations like the one I showed you, you will find that a lot of people are using that equation of a state. However, well, this is the thing. Neutrons or nucleons, neutrons and protons don't behave as a Fermi gas that is not interacting. They are very strongly interacting. So what we would like to do is to understand if changing the equation of a state will tell us something about a star. And yes, it does, right? For example, this is the influence of an equation of a state. This is something that if people here are doing general relativity, probably they are very familiar with this. Is the mass radius diagram. And in this work, we took 3 different equations of a state, and each of them reproduce this different line. And by that, I mean that interactions between the nucleons were changed. And then, you know, the equation of a state is predicted. This line here tells you what is the maximum mass observed in this year for neutron stars. And all of 3 equations of a state reproduce it, which is something we want to happen. And here, for example, we have if neutron star has a mass of 1.35 solar masses, what will be the radius predicted by this equation of a state? And you can see there are one that is around 12, and the other one is the maximum will be around 15. The one that has the smaller radius is called the soft equation of a state. The one that predicts larger radius is called the stiff equation of a state. And you can understand that because it means that for the same mass, you have put much more in a smaller volume. So it's soft. It can accumulate much more matter. Okay, so soft and stiff, a couple of concepts that I need you to keep in mind for a bit. Okay, so now that I have all those kind of things, some questions come to mind, and it's like, okay, how will neutrinos interact in this very highly dense environment, right? So a neutrino will scatter in a neutron star or the formation of a neutron star or in neutron star mergers in this very dense environment, and it's not going to interact only with one neutron or one proton at the time, but with all these correlated particles. So that's one question. The other consideration is that neutrinos oscillate between matter states. So how is the oscillations, what we could learn about oscillations from neutrinos, observing neutrinos. And the other part that I also need to understand is that once neutrinos leave this dense environment and they can travel long distances without interacting with anything and tell us a lot of things, still there is a very dense compact object, and neutrinos are being subjected to this strong gravitational field. I'm not going to talk today about neutrino oscillations. I don't have time. But I want to talk about the other subjects. So this one is a cartoon that I made. That's why it's like all funky. So we can talk about neutrino interactions a little bit. And I just pause in here so you know. We stretch. OK, so neutrinos are generated in a supernova or in a merger because the temperature is so high. This is how they generated, okay? They are generated here. They go through these reactions with protons, neutrons, electrons, and at some point, their matter is not so dense anymore, so they don't interact and they decouple. We can find here some plane or some center or whatever you want and measure the distance for each neutrino or these densities for neutrinos to decouple. And if you think about a 3D environment, that will define a surface. Okay, so for a supernova is the neutrino sphere. For whatever other surface or environment will be just a surface. Neutrinos undergo these reactions. In the charge current reactions, neutrinos are not seen afterwards, and in the neutral, they remain the same. Okay, so if I do that and I just study one simulation or as many as I want, I have 2 different examples here. I have, for example, a disk, a torus that was accreting into a black hole. That could be the scenario after a neutron star merger. The merger, the central compact collapse, central object collapsed to a black hole, and there is matter around it. And this was a steady state scenario, so we just cut it in half here so you can see what is happening, but you can imagine the rest of the donut. Notice the temperature. Here is a neutron star merger. The 2 neutron stars were of 1.3 solar masses, and with a soft equation of state, and then you can see also the range of temperatures. So the neutron star, the neutrino surface will tell me a lot, because then I will get to know deep inside from this object where neutrinos decouple in terms of height and then the local temperature. And with that, I can build a spectrum. With that spectrum, I can take that information and try to see if I can detect them on Earth, or what I predict that I will detect on Earth. And that is useful because I can dig in the current data that is taken. If some other observatory finds a peak in the neutrino counts, then I can try to see what was the initial source that produced them. Okay, as I mentioned before, this was a cartoon where the neutrinos now were interacting with one nucleon at a time, but I already mentioned neutrinos are not free in their environment. If you were studying neutrinos scattering only from one neutron or one proton, then these numbers, SA, SV, which are called the structure factor, will be equal to 1. SA and SV tell us the interactions between nucleons, how they are correlated, and they transform the cross-section in this way. Okay, so if I have a model for the nuclear interaction, then I can change the cross-section. That changes the time or the point where neutrinos decouple from dense matter. So I just preparing this work with a student well, he already graduated, so we are still working on this. So, but stay tuned. Okay, we took this simulation, okay, and then we put a lot of different nucleon interactions, okay, a bunch of them, and then we try to see if there are differences in the neutrino surface. And I know that I'm not going to discuss each of them. I just want you to notice that there are a few differences between them. And I know this may be, I don't know where this is going to lead me, okay? I don't know, this is work in preparation, but where I can see is that there could be a difference in one plane at least that we have tried of 2 kilometers. Now, if these 2 kilometers represent a big gradient in temperature here, then I get to know something about distinguish between different nuclear interactions, because I will be able to determine a different spectrum. It can be interesting for that. It could be interesting because even 2 kilometers away from a black hole can make a difference, can make a lot of difference. We are in around a very compact object. It's not the same for neutrinos to get free 2 kilometers under or above. And I'm telling you why. Like, look at this. I'm trying to make a case here as well, where we calculated the number of neutrinos, the neutrino flux, as a function of the energy when we were above, in this point above this accretion disk, okay? And then we took 2 effects for calculating these fluxes. One, that neutrinos don't travel in straight lines when there is a black hole around them. Just as photons get deflected, gravitational length, the same thing is going to happen with neutrinos, and that produces enhancement here in these peaks. And also we took into account that the energies are going to be redshifted, okay? And the difference between the two of them are, like, for example, if you compare what is the red line here, okay, the solid red line with the solid black line, and you see that at higher energies, well, the neutrino flux was reduced by taking gravitational effects into account. Oh yes, I know that the gravitational effects are important and the neutrino fluxes are, you know, affected, but what for? I mean, what is the point? The point is, remember I told you that we can go from silver to gold in neutron star mergers, that was seen. Well, if there are a change in the number of neutrinos, indeed there are going to be less heavier elements, or at least the heavier elements are going to have a shift. So this is what I'm trying to say. And this is an extreme scenario. So this is like a, you know, what would be the worst case scenario? Here the crosses, this simple, are solar abundances. These are observations. This is mass number, this is abundances. And if we take the same astrophysical scenario, but we don't include any relativistic effects, then, you know, Newton would have predicted these abundances. But the red line shows how powerful the general relativistic effect can be for neutrino in terms of the abundances. Okay, so again, this is an extreme scenario, but we could study much more, and that's the point. That's the point, to keep studying this. So I guess that so far some remarks. I'm mindful of the time. I have many more stories to say. So I have to be careful about which one I'm going to focus on now. But a little bit to get the attention to the next step, let me summarize, is that the neutrinos are able to change the neutron to proton ratio, and that changes the abundance of elements, and then we can see that effect. And that neutrinos don't interact with one nucleon at a time. They interact with a sea of them correlated. If we can measure them, detect them, or something like that, then we will be able perhaps to constrain models of the nuclear force. So these are two aspects that I want to focus on. I just wanted not to focus, I already focused, but to let you there. Okay, I'm going to skip this because I don't think I'm going to have enough time to talk about neutrinos and the question of a state. But I want to talk in this here today about relic neutrinos. And the reason is because this is some work I would like to keep exploring, and I think there could be synergies going on here that have potential. Okay, so all this nice, we can probably detect neutrinos from mergers. With the current capabilities of super K, maybe it happens. We could see as far as the galaxies, satellite galaxies, with hyper K maybe beyond that, but neutrinos for mergers are rare to happen. Okay, from supernova, one every century, from mergers every 10,000 years. So why not to look at neutrinos that have been ever produced since the first neutron star mergers or accretion disks form? And right now they're permeating this space and are right there and are being recorded in data right now at neutrino observatories. So similar concept as the cosmological microwave background. So what happened with those relic neutrinos? And the results I'm going to show you here correspond to accretion disk neutrinos. And so I'm going to take 2 seconds to explain what are the possible formation scenarios. So one is from neutron star mergers or a merger of a neutron star and a black hole. As matter is pulled out from a companion, then as I already mentioned, there could be a black hole and an accretion disk around it. The other scenario is the collapsars. And collapsars can be formed when very, very heavy stars don't go to a supernova and just go immediately to a black hole, okay? Because the initial mass is so high, neutrons won't provide this external pressure to keep it away from gravitational collapse. So essentially, what we will have is that matter goes immediately to the black hole, but won't sustain a disk unless the progenitor has initial angular momentum to have some matter accreting around it. So that's the collapsar scenario, and collapsars are being suggested as an art process scenario site. Okay. Is it worth studying? Is it? Well, it is in my view for the following reasons. So here I'm having the spectra of neutrinos. This is the supernova spectra, okay, and it's very well known, okay. Oh. But I also have the spectra for collapsars. Some here come from neutron star mergers, some others didn't think about just the source, just assume some black hole is already existing and has an accretion disk around it. So you can see in this range of energy, the supernova spectrum is lower than the accretion disk scenario. And you know, our powers actually in other ranges here. So it could be, it could be. Okay, so what do I need I need to study these neutrinos, to make a model of these neutrinos, I need a bunch of physics that I'm not entirely familiar with. And this is what I call you or whoever could be interested here. I know how to calculate the neutrino spectrum, okay? I get the temperature, the neutrino surface, blah, blah, blah. But then I need to understand better what the event rates, meaning how the first star, dense stars form, how they merge in cosmological times, or how the collapsars form and how they evolve in cosmological time. And I need to also understand that the universe has been expanded, right? So this could help me also to understand, the better the models I have here, the more accurate I could be about the neutrino fluxes. Okay, so fortunately, there are some groups that are putting a lot of effort in finding the event rates, the neutron star merger rates, because of interest with LIGO. And here I just put here some observations that come from predictions from gamma ray bursts for the case where a supernova just go boom to a black hole. There is no the typical neutron star formation scenario. And these are for rates for mergers of neutron stars or black holes with a neutron star. There are many predictions here and depend on the model of how the merger really happened. I took the best case scenario and the worst case scenario, and I applied this with some specific model for the collapsar or the accretion disk. How fast is the matter being accreted? 1 solar mass per second to 9 solar masses per second. And then I can kind of build what I would say in my terminology. I'm borrowing stuff that is not probably the right way to say, but I can find some uncertainties or a band that tells me, okay, most likely the number of neutrinos that I will detect in super K, given that model of relic neutrino background for accretion disk, will be in this range. So here it's very easy once you know the relic background to convolve it to the detector that you have at hand. It could be Snow Lab here instead. For example, a lead-based detector. Here I made calculations for water Cherenkov detector, and I was assuming a super K, meaning with 32 kilotons of water, okay? Oh boy, this is a lot of information to take, but look that this is the relic neutrino that is being calculated for supernova. This is something people already know, nothing new. And this is our models for accretion disk, and you can see that is comparable. So at the minimum, in the MEV region, we will have neutrinos that are relic neutrinos that are coming from these sources, supernova, collapsars, neutron star mergers, and that we need to keep into account for any other detection, or maybe to get some physics, more physics out of it. I leave it up to you. How do you want to interpret this? But the last point I want to make, because I want to have questions and show you, I don't know if more, but point is that I know that in my lifetime, a next merger in the galaxy is not gonna happen. That I know, okay? But if I start looking for the diffuse neutrinos, I know they're been already there. I know they're in the detector. I know there are tapes, okay? So if I search in the past year in super K, I predict that should be from 0.1 to 25 neutrinos coming from collapsars. That's what I'm guessing here with a very rough estimate. I'm not making sensitivity of the detector or anything. I need to talk to you, essentially, the experts here, okay? I don't know because that's not my expertise. And from neutron star mergers, the best case scenario will be around here, okay? So, okay, in 5 years, maybe not that good, but if I take a hyper K in 10 years, well, maybe I will have in total 900 from collapsars from neutron star mergers. And this can happen in my lifetime or in a grad student lifetime. right? They graduate, they leave, 5 years, nice project, and that's it. Okay, I'm gonna stop here with some conclusions, because I know I have more material that I skipped, but before I totally lost you in trying to explain more stuff, I think it's wiser to just stop and leave you with my conclusions. So it's a very exciting area for synergies, for neutron star mergers, for astrophysics, for neutrino people, and because we have many tools now that a lot of data is coming and we need to understand it better. Yeah, I guess I'm gonna just flash my collaborators. Thank you, Enser. Thank you, and then I leave you with the conclusions there. Thank you.